8.8 LOpps. All right, I'm going to explain every problem that was due for Monday, February 15th. This material is on the upcoming test. Number 15, the integral from 1 to infinity of 1 over x squared dx. First of all, we need to change that. The limit as b goes to infinity from 1 to b of x to the negative 2 dx. Anti-differentiate that. That gives us negative x to the negative 1, which we know negative 1 over x from 1 to b. I'm going to keep that negative outside. Actually, I could have brought it way down here to the front if I wanted to. 1 over b minus 1 over 1. So that's the negative of 1 over b minus 1, but I can now use that negative and switch the order and make it 1 minus 1 over b. And as b goes to infinity, I get 1 minus 0, which is 1. So this converges. Number 17, the integral from 1 to infinity of 3 over the cube root of x. We want to write that as, I'm going to bring that 3 out, write it as x to the negative 1/3. The limit as b goes to infinity from 1 to b. Anti-differentiate that. That's going to give us x to the 2/3 with a coefficient of 3/2, which I'm going to go ahead and bring out in front. The limit as b goes to infinity of substitute b minus substitute 1. Now, as b goes to infinity, this is an infinite number to a power which is still infinite. So this diverges. 19, the integral from negative infinity to 0 of x times e to the negative 2x dx. We are going to do integration by parts for this one. I'm going to let my u equal x, so my du is 1. My dv is e to the negative 2x, makes my v negative 1/2 e to the negative 2x, and I can use the tic-tac-toe method because I'm letting my u be x, which will eventually have a derivative of 0. So e to the negative 2x, the antiderivative, negative 1/2, e to the negative 2x, the antiderivative, 1/4, e to the negative 2x. So this becomes positive times x times negative 1/2 x e to the negative 2x. Negative times 1 times positive makes it negative 1/4 e to the negative 2x plus c. Of course, we're going to be doing a definite integral, so we don't need the plus c. And you will notice I did a little bit of creative algebra here. I looked at these two terms and recognized I could factor out a negative 1/4 e to the negative 2x. When I factor that out, that leaves a positive 2x here and a plus 1 here. So this is my antiderivative. So here we have the negative 1/4 is here. Limit as b goes to negative infinity, e to the negative 2x times 2x plus 1 from b to 0. Substitute 0 minus substitute b. Now we know e to the 0 is going to give me 1, so this is going to be 1. Minus. Notice that b is going to negative infinity, but this is e to the negative 2 times b, so that's e to the infinity. And that right there takes care of the rest of the problem, because what I get is 1 minus e to the negative 2b, which makes it e to the infinity times infinity plus 1, which is still infinity. I get, important, negative infinity. Now, why negative? This is 1 minus times minus is plus times the negative out here. So we are going to diverge. So 21, 0 to infinity, x squared, e to the negative x dx. We're going to go through the same process of integration by parts. And this one, again, I can use the tic-tac-toe method. So here we are going to get this expression when I anti-differentiate. And notice we can factor out a negative e to the negative x from each term. Makes it just a little nicer to deal with. The limit as b goes to infinity of negative e to the negative x times the quantity x squared plus 2x plus 2 from 0 to b. Substitute b. Substitute 0. Now, this negative sign can come out here, which is what I did. I wrote this as e to the b down here. And we can see that we have b squared plus 2b plus 2 over e to the b. Exponential increases more rapidly than polynomial. So this is going to become 0. Minus 2 with the negative in front gives me 2. But let's look a little more closely at this. This is a L'Hopital's rule situation. Notice that the numerator, as b goes to infinity, this would go to infinity. The denominator would go to infinity. L'Hopital's rule applies. So I get the derivative, which is 2b plus 2 over e to the b. Again, I have indeterminate form. The top goes to infinity, the bottom goes to infinity. And remember, we want to write it like this, not like this. Do not do it like this on AP exam. Multiple choice, no one's going to look at your work, that's fine. Free response, do it like this. Okay? And again, L'Hopital's rule applies. So taking the derivative gives us the limit as b goes to infinity of 2 over e to the b. And now you can see why this is 0. Okay, number 23. The integral from 0 to infinity of e to the negative x cosine of x dx. We are going to integrate by parts. Our u is e to the negative x. Our du would be negative e to the negative x. dv would be cosine x, so v is sine of x. Here is our integration pattern. We cannot use tic-tac-toe method. I'm going to tell you this is very similar to lecture manual, page 33, example 3, where we had e to the x, maybe sine x. Okay? Going to be the same process, except a little different with the negative sign. All right, so here's my u times v minus the integral of v to u. We've got to do it again. I'm going to take this one right here, and I know that I'm going to, again, let my u equal e to the negative x. And so my du is negative e to the negative x, so my dv is sine x, and my v is negative cosine x. So we have, for this, u times v minus the integral of v du. Now, I can bring this negative here, and this negative make this positive, and that leaves a negative out here in front. And notice, on both sides of the equation, I have the integral e to the negative x cosine x dx. So let's just add this one over to the left-hand side. You probably remember when we did that in class. It was actually one of the videos. And now we can divide by 2. So finally, what we now know is this integral up here at the beginning of our problem becomes this. So now we can we have anti-differentiated, and we can evaluate our integral. So finally, the limit as b goes to infinity of 0 to b e to the negative x cosine x dx is 1/2. The limit as b goes to infinity of e to the negative x can come down here, over, take sine x minus cosine x over e to the x from 0 to b. You could have left it e to the negative x, that's fine, but this makes it nicer since we're going to infinity, because I can see what's going to happen in my denominator when I'm looking at e to the b. So 1/2, limit as b goes to infinity of sine of b minus cosine b over e to the b, minus sine of 0 minus cosine 0 over e to the 0. Now, here's what I know. We know that sine and cosine are bounded by 1 and -1. So my numerator is always going to be something between -1 and 1. Never going to get any larger than that or any smaller. And so the top is going to be that number. The bottom, as b goes to infinity, gets very large. So this becomes 0. Sine of 0 is 0. Cosine of 0 is 1. So I have negative, negative 1, which makes it positive, times the 1/2. So I get 1/2. So this integral converges. Number 25. The integral from 4 to infinity of 1 over x times natural log x cubed dx. First, I'm going to write this as the limit as b goes to infinity from 4 to b. Natural log x to the -3, 1 over x dx. Notice you have u to the -3 du form. Since we have that form, we know that we are going to be able to anti-differentiate this to u to the -2 over 2. That is going to give us limit as b goes to infinity of negative natural log x to the -2 over 2 from 4 to b. Now, I'm going to bring out the -1/2, and we're going to look at this. We're going to substitute b in minus substitute 4. Okay, as b goes to infinity, this is infinite. I get 1 over huge, which is 0, and I get negative 1 over natural log of 4 squared. So I have this negative times this negative, which gives us this. But you go look the answer up in the back of the book, and this is not the answer. So what can we do? Well, we can simplify natural log of 4 to be natural log of 2 squared. It is still being squared. This 2 can come down in front of our natural log. And notice that this is 2 times the natural log of 2 squared. Well, that 2 squared is 4 times the 2, which gives you the 8, leaving the natural log of 2 quantity squared down below. Wow, tricky, huh? All right, 27. So our improper integral here, the problem is 0. We need to separate. I can't go from negative infinity to infinity, so let's pick a number, and 0 is always a nice one when you can use it. Now, what you should recognize here is you have arctan u form here, right? Your u is x, your a squared is 4, so your a is 2. So these are 2 times arctan u. So remember that when you anti-differentiate in the arctan u, it is 1 over a arctan u over a. So I have 2 times 1/2 arctan x over 2 from b to 0. That's this integral, where b is going to negative infinity. Then plus the limit as b goes to positive infinity from 0 to b. And this one, again, anti-differentiates to 2 times 1/2 arctan u over a from 0 to b. Now, evaluating, notice the 2 times 1/2 goes away, so I have something nicer to look at. Substitute 0, substitute b, plus 2 times 1/2, substitute b minus substitute 0. Now, this is where this gets tricky. b over 2. As b is going to negative infinity, it's just like saying as the angle goes to negative infinity. As we are getting to negative infinity, what is my angle getting close to? Negative pi over 2. So this gives me 0 minus negative pi over 2. What about over here? As b goes to infinity, this would be arctan of infinity over 2, still at infinity. So what angle as tangent goes to infinity am I getting close to? I'm getting close to pi over 2 minus 0. So I have 0 minus negative pi over 2, which is plus pi over 2, plus pi over 2, which is pi. You'll notice the little hearts all around 29. I like this one. It is going to be similar to lecture manual page 31, example 6, and you also did homework problems like it in section 8.1. So the first thing that we have is 1 over e to the x plus e to the negative x. Sorry, I'm having lighting issues here since I'm at home. Maybe that'll work. So what we're going to do is if we multiply by e to the x over e to the x, we get this. I get e to the 2x plus e to the 0, which is 1. Now, look at what we have here. If my u squared is e to the 2x, that makes my u e to the x. Look at this, I'm looking at an arctan form here. A squared is 1, makes a 1. if my u is e to the x, my du is e to the x dx, which I have, so I actually have du over u squared plus a squared form, which integrates to 1 over a arctan u over a. So once again, we're looking at an arctan problem, which is why I like this one so much. And we get 1 over a, which is 1, so arctan of e to the x. Substitute b minus substitute 0. E to the 0 is 1. Arctan of 1, the angle whose tangent is 1, is pi over 4. The angle whose tangent is infinite, that's pi over 2. So pi over 2 minus pi over 4 is pi over 4. It's very nice. 31, a nice and easy one, 0 to infinity, cosine pi x dx. My u is pi x. My du is pi times dx. Very easy to fix this integrand. And so I have 1 over pi cosine pi x pi dx, which anti-differentiates to sine of pi x from 0 to b. Going to bring that 1 over pi out in front, deal with it later. And now we have 1 over pi, the limit as b goes to infinity of sine of pi b minus sine of 0. Now, sine of 0 is 0. But what about pi b? As b goes to infinity, you know that sine looks like this. So as we go to infinity, we know that sine b is bounded between -1 and 1, and we're not approaching a single value at all. So this integral diverges because while we are bounded, we still are not approaching a single value. Now 35 was a late entry in the homework problems, but it's a good one. So I wanted to go ahead and do it. If you didn't do it, well, you might want to have a looky-loo. So from 0 to 8, 1 over cube root of 8 minus x. So we're going to fix the integral. I'm going to write this as 8 minus x to the -1/3. If my u is 8 minus x, my du is -1 dx. So I'm going to adjust for that. Okay, we know that u to the -1/3 is going to anti-differentiate to 3/2 u to the 2/3. So this will become, negative comes out in front. What makes this improper is x cannot be 0. So we have to approach 0 from the right. So we haven't done any of those problems, which is why I like this problem. So 3/2, 8 minus x to the 2/3, evaluate from b to 8. Substitute the 8 in, substitute the b in. 8 minus 8, 0. So 0 to the 2/3, 0. So that one's easy. This right here, as b goes to 0 from the right. Hey, as b goes to 0 from the right, that's 0. So what I have here is, notice that this negative here and this negative here become positive 3/2. 8 minus 0 to the 2/3. 8 is 2 cubed. 2 cubed to the 2/3. The 3's cancel. So I have 3/2. 2 squared. Here's a factor of 2. Take away one of these factors of 2, so I have 3 times 2, which is 6. Nice problem. It's one of these where you have to look at 0 as we go to it from the right side. So I should have assigned some of those, and I neglected to. So there you go. This was a late assignment. Hopefully you saw it, but whatever. All right, let's look at 39. Number 39, what you need to remember, 0 to pi over 2, tangent theta d theta is tangent, has its own integration rule. And we know that as we go to pi over 2 on tangent, we're going towards an infinity. So we need to write this as the limit as b goes to pi over 2 from the left-hand side. And then we're going to go ahead and anti-differentiate it. I really should have done this first. The limit as b goes to pi over 2 from the left of 0 to b, tangent theta d theta. I should not skip that step. And now we have this. And we're going to evaluate, substitute our b in, substitute our 0 in. Now, just a reminder what's going on here, right? We know secant of 0 is 1 because cosine of 0 is 1 and secant's reciprocal. If we just look at a little graph of cosine, we know cosine looks like this. Where cosine is 0, on secant we will have a vertical asymptote. So as we approach pi over 2 from the left on the secant graph, we're going towards infinity. So this becomes infinity minus 1, so it's infinite, so we diverge. And I have a big whoo after all of that. That was a lot of work, okay? So you probably, with us not being in school, got a better situation here because I explained every single problem thoroughly. Hope that helps you. Go on to the 9.1 and 9.2 TP's video.